let us then kind of turn our attention to some other matters at hand. Okay, let's go back to 3D. We'll see how this looks. So I got my building hanging around over here. Let's go ahead and look at the structure only. Zoom to fit. Let me turn off those walls again. Looking pretty good. My building's looking fine over here. It's got all sorts of floor support. It's got some roof support. It's got columns. Loads are hopefully coming on down to the ground, although we should put a little structural support down there to make sure that we're not overstressing the ground. However, my building's in trouble. And my building's in trouble for the very reason that so many buildings collapsed during earthquakes. And that it's kind of got all these nice sticks that are kind of pointing up, but as soon as anyone just pushes a little bit on the side, it's highly likely it's going to go, and it's going to tilt, stuff like that. We need to provide a little bit of lateral support. So let's talk about that. Because lateral support, ever so important as an issue. We're very aware of it here in Northern California because of the whole notion of the earthquakes. We're very aware of it when we're doing tall buildings because of the wind and the wind forces, which actually need to be much stronger as an effect than the earthquakes. But, you know, either one of those two forces could dominate. What it really means is that we have to go through and kind of brace the building for something that's happening sideways. It's interesting. Gravity loads are actually relatively constant. You know, the weight of the building and us dancing around in it, that's, you know, most of the time. Snow on the roof every once in a while, but it doesn't change drastically. You know, earthquake loads, you gotta picture this. You know, one day you're sitting there, perfectly happy, and someone just comes rushing at you, 100 miles an hour, and just pushes as hard as they can sideways, and you weren't even ready for it. And, you know, you have to respond to that. And most buildings aren't really so ready for that. It's really kind of this big jarring impact, kind of came out of nowhere, and you have to be ready for that. Because really, here's how it sort of works. You have this force is pushing sideways, and what happens is, basically, as the building is pushed sideways, all the dead weight of the building, all that tile on the roof, everything up there, you know, it's basically going to resist and whip back. You know, it really gets down to the dead load of the building. And really, the amount of force you have to resist is really based on the dead load of the building. And here's what's going to even sort of worse about it, is this whole notion that, you know, as you move down through the building, okay, you got this dead load of the roof, and the roof tends to be a pretty big dead load, especially with a lot of tile on it or something like that. Super. So between the roof and the first floor, or the second floor, okay, you know, that floor level has to resist basically the roof load moving back and forth. Okay, accelerated by the earth, because there's inertia and, you know, there's a resistance. Okay, the first floor, it has it even worse, because the first floor not only has to go through and resist the roof load, it also has to resist the load of the second floor's dead weight. Okay, so it's all the load from up here plus the load from down there, so it gets worse. And the taller the building, the worse and worse it gets, because every successive layer has to not only carry its own load, it has to carry the load of everything that's up above it. So as we think about lateral systems, you know, it's tough in that you have to go ahead and provide the support, and often you have even more and more lateral support down near the bottom of the building because it has to take care of all the force above it. So we got a problem, but we have ways to deal with it, so let's kind of talk about it. Okay, here's the deal. When it comes to resisting those lateral forces, those forces that are pushing sideways, and stick things do, they fold. This comes, do that, yeah, because there's no resistance. There's two big ways to approach it. One big way is, well, we got to provide some resistance. One way we can do it is with some sort of structural framing elements that we typically call braces. And we can put those in, and let's kind of show you what they would look like. So just so you know, as we go through and think about our building, okay, let's look at it in the floor plan view. Basically, we have to resist the lateral forces on each of the different sides. So we have to resist them in the back wall, we have to resist them in the front wall, we have to resist them in the side wall over here, and we have to resist them in the side wall over on that side. Now, so at the bare minimum, we have to kind of do that. We have to have reinforcement in both directions. Okay? It doesn't have to strictly be at the exterior wall. But depending upon the length of our building and size of our building, it may be enough just to do the ends, but you may have to actually put some in the middle too to also go through and resist it. It's really this whole notion of you need to have some sort of resistance. Actually, let me even draw this. That might be easier. See if you get the rules down. So we'll start with a simple case. These are my walls of my building. Okay. As I'm going through and I'm putting a lot of load on the building. Okay, picture this. If you can picture the floor of the building or the roof, either one of them, acting like a big beam. So picture this floor almost as though it's a big beam like this to resist all that load. What has to happen is we need to provide some resistance. Half of it's going to come from this. Half of it's going to come from this side. Okay. So it's kind of like simple beam mechanics, that kind of stuff. Okay, super. That's pretty good in terms of doing that. In terms of where that resistance comes, usually what we'll do is we'll put some sort of bracing in the walls. So I could put that bracing over here. I could put that bracing over here. I can actually put it all the way back there if I want to. It really doesn't matter a whole lot. Just somewhere along the line, we need some bracing to go ahead and provide that resistance if we believe that, like a column, that's not going to collapse. Okay, but generally, it's pretty well braced, so we don't have to worry about that. So we're going to put some resistance that way. In the other direction, because we're never quite sure how earthquakes are coming, all this force could be coming this way. So we got to think about the building being a big old beam going that way. So again, we need some sort of resistance on this angle. We need some resistance on this side. Okay? And depending how strong that floor frame is, okay, we may need some resistance in the middle, because if it gets to be too awfully long, that may be too skinny as a beam. It may not have enough resistance. We might actually have to go through and put some resistance somewhere in the middle, just so we can sort of shorten the span between those two different loads so we have less deflection. Okay, so at a high level, it's a really quick explanation about lateral loads and how we go through and resist them. So often what we'll do is we'll put sort of the lateral resistance at the outside edges. That's kind of typically a good way. There's usually a wall out there someplace to put it. But very often we end up having to put it somewhere in the middle too. Just a little bit of resistance somewhere in there. And we'll talk about that in a second in terms of cores and why we have cores in buildings. Okay, so I need to get some lateral resistance, and I have a couple different ways I might approach it. Let me go back out to that structure. Okay, I'm looking at the back of the building over here. I can approach it in a couple different ways. I have these really kind of like nice frames of steel going on here. If I wanted to stop that steel frame from racking over, there's a couple of ways I might approach it. Okay. If you have a frame and you want to stop it from moving, okay, what are our options? What can we do to stop that thing from moving? How can we add braces to it? Yep. So one thing is to do something like that. Okay. Another way is to do something like this. In fact, if you go over to like the Wong basement, you'll see a lot of that kind of hanging around inside the building. A third way we might do it is to actually go through and really reinforce these corners and make sure those are incredibly rigid. Okay. So, with those three strategies, you have the K-brace, the X-brace, or the ever-popular moment frame. Let's think about those three different strategies. Well, actually, let's talk about another one. That's really gross. We could just fill it in entirely solidly. We could make a big panel out of that, as opposed to being kind of a loose frame of things. Okay? And that's typically what we would call a shear wall, or shear panel. Okay. So you got your main tools for resisting lateral loads right there in front of us. So let's talk about each of them and how you might model them and the advantages. Okay. K-braces. A lot of people understand K-braces. K-braces are actually pretty easy to work with. For example, in our steel frame building here, we could go ahead and run some steel from the base of these columns up to the center of that beam and really make a K-brace system. And that's going to work out just fine. That is A-OK. I could go through and go to the Structures tab. I can say, let's grab some braces. We choose a material for our braces. Oh, that wide flange 12 by, that sounds awfully big. I'm going to go for some like tube steel or something like that. That might be a little kinder. So I'm going to go structural framing. And again, not to worry, we'll figure out how to size these. HSS, thank you so much. Hollow structural sections. Let's go for some 4x4s or something like that by 5/16. Yeah, 3/8. Again, we'll figure out the sizing. So I got some hollow steel. What I can do now is, I'll go from the bottom here. I'll go up to the midpoint of the beam. See if I can get to the midpoint of the beam. I'm very bad about snapping sometimes. Oh, there it is right there. Oops. Boom. I'll snap it down there. Now again, you're going to say, hey, that looks kind of wonky. That's not right. Yeah. Analytically, it's right. Graphically, it's not looking so right, but that's okay. We can fix that. You know, ultimately, we'll do something there to cut off the tubes and cope it and put the haunch in and stuff like that. But how do I know it's analytically right? Because if I actually go back to the analytical model and look at it over there, I can sort of see that's actually looking pretty good in the scheme of things. That's not too bad. Okay. So I got a K-brace there. Let's kind of zoom on out. At my first floor, that may be sufficient. You know, that may be enough to go through and kind of just have it on that one side. I might want to also put one over there and split the load. That would actually help us with a little bit of symmetry. Very often having all the lateral load on one side of the building kind of introduces funny torquing, and that's not so happy in terms of what could happen. So maybe I'll put one over there too, and that would allow us to split the load. But architecturally, what you end up having to do is just kind of think carefully about really where is the best place to go through and put these. Bracing, bracing, bracing. I'll go from here up to there somewhere. Sometimes I have a hard time finding middles. I should snap. There we go. Okay, and that'd probably be a little bit better. Okay, in the scheme of things, see any problems with K-bracing? K-bracing, it works very well structurally in terms of that. How about architecturally? What's that? Yeah, it could be you. In fact, as I think about my building, I probably wasn't very smart about this because if I go back to my building and go rolling around back over there, I conveniently went ahead and put those K-braces just right in the middle of like my big glass view, so that probably wasn't a very smart move. So structurally, or architecturally, it probably would have made more sense to go through and put them somewhere here in the middle, behind all that closed panel, and that's okay. Again, as long as we sort of keep it balanced, we're going to be okay. There's better, yes?
If your structure is inside of the architectural facade,
yeah.
So you're just having the K-brace like in the middle of the room, essentially?
Yeah, it's actually in the room a little bit. What will often happen is it'll get sort of enclosed by something so you don't have to look at it. Even in this building, if you want to see the braces, go to the copy room right behind me here. And you'll actually see them coming on down. There's this big diagonal brace coming through. Or if you go into the long basement, go right to the center of like a big student area where we're working, like kind of under X, and you'll see them all kind of hanging there in the entrance. So sometimes you leave them exposed. You know, it could be architecturally interesting. Sometimes you hide them. Kind of depends on what you want. I kind of like keeping them exposed, but you got to sort of think. But K-braces do have that thing of, well, you know, they're just kind of, they're there. They're in your space. So let's go ahead and go back to the structure only. So K-braces aren't too bad. Another way to approach it, ever so closely related, is the ever popular X-brace. So how do X-braces work? X-braces would work, although I should probably do something. It probably wouldn't be a great solution here because I should put a steel beam up there to really make it work nicely. But I'll put something across there and put something across there. Now again, that looks like it's just kind of crossing. There would actually be some sort of a connection in there with 4 different tubes kind of coming off of it. That's actually how it's done over in Wong. So now, ultimately, is there a lot of difference to you whether it's a K-brace or an X-brace structurally?
Yeah, the X-brace is more efficient.
Okay, just sort of a better shape.
Yeah, the K-brace, you put a lot of load in your beams. You have to make bigger beams.
And then have them carry, yeah, okay, whereas the X-brace, it actually is all sort of handled just on the endpoints. Okay, so X-braces can work. X-brace, you know, it's a little fabrication to go on there in terms of that, you know, but you know, they're actually, again, a very good solution, so a lot of times we use X-braces. And that's probably the most common thing I see. It's like X-bracing kind of hanging around. Yeah, so we're pretty good in terms of what's going on here. Either of these ways, they're probably pretty similar in cost, kind of pretty similar in terms of visual impact. K-braces may be a little bit better in that you have a kind of a part that isn't so obstructed versus this. It's pretty much squarely in the middle of the bay. That's not so good looking. Okay, but either of those methods work out pretty well in terms of taking care of things. Okay, you add a little extra steel. Everything's put together nicely. Okay, let's go popping around to the other side of the building. Kind of more interesting out here. This is, for example, where I have these giant columns that are coming all the way down from the lower kind of patio area all the way up to the 3rd floor. Okay, so I could go ahead and put a big X-brace there, a big K-brace in there, but that might be more architecturally impactful, so I may not like that so much. Okay, so then I pull my 3rd trick out. Okay, I can actually start thinking about a moment frame. Let's talk about what a moment frame is. Okay, moment frame, let me go ahead and I'll just put it right in the center here. I'm ultimately going to put a piece of steel there to make it work, because it is going to require steel. Here's what we're going to do. We're going to take that piece of steel up here and these columns over here, and we are going to weld the hell out of them. We're going to go through and put all sorts of like steel reinforcement in here, weld it all together, and make something that is so incredibly rigid as a big U-shaped frame that it is not going to allow any movement in the case of these lateral loads. Okay? And we can do that. You know, you'll see, oh, incredible double wall, multi-layers of plating and kind of welded reinforcement here, and they come on out to the site and kind of erect it there. What happens is this thing typically gets erected or welded out in a shop somewhere and kind of, you know, brought out to the site in a big frame. Yeah, it's kind of a nice way of doing it from the standpoint of visually, it's very low impact. It kind of takes care of the loads in sort of a nice way that doesn't sort of impinge on the architecture at all. But, you know, trying to carry everything through a perfectly rigid frame that's going to carry all those loads is a sort of an expensive thing to do, and it puts an awful lot of structural loading on that thing. So this whole frame itself may be one of the most expensive structural elements you're truly working with. But moment frames are there when you need them, and use them judiciously. They're kind of, you know, it is there if you really need to go ahead and kind of keep things open. It's just sort of another way of doing it. And as we specify them, it's really not all that different. Let me kind of show you actually where they live in the scheme of things. As we think about this you know, model and how it works, I just put a piece of steel in there. It doesn't look too awfully special so far. It has these start and end connections. I can say that it's a moment frame right there. Okay, and that'll be enough to basically say that analytically I want to go through and treat it a little bit differently. That it's not just going to be a pinned connection of some time. It's going to actually have some moment resistance to it. So moment frames, again, pretty good as a way to do it. Okay, although expensive. Okay, third way we might approach it is, look over here. I don't really have much to work with on that end wall in terms of what's going on. You can start thinking about using wall panels. And wall panels, again, can be sort of very, very good for doing this. There's a lot of different types of wall panels you can use. You can use concrete wall panels, which is sort of very efficient because you can sort of, in the concrete, embed a lot of steel, and concrete's actually pretty good when it's reinforced without resisting the lateral forces. You can actually even have like steel shear panels called hardy frames or strong wall panels. They have these different sort of hybrids that are available to go ahead and resist lateral loads. But if you want to put some sort of a structural shear wall in there, let's talk about that. How it would work is something like this. I'd come over to, let's say, level 1. And somewhere in that wall, I'm just going to cut out a section of it right here, just so I can sort of change it. Well, I could put it inside if I want to. I don't actually have to put it in the facade. You can sort of decide either way you want to go with it. But if I want to put it right in the facade, what I'll do is I'll go through and architecturally, what am I going to do? Let me choose the wall. Let me go through and cut some section of it. And say that some section of that is not going to be strictly just the artificial surface. It's actually going to be concrete. Put concrete in here somewhere. There it is. Some sort of concrete wall. We can fix that up so it looks right from an architectural standpoint. So over on the sidewall now, you have some sort of hybrid of materials. What I have to do is, though, run this all the way up. It's not good enough. Well, you can sort of break them, but the more common thing is to actually go through and have these run all the way up to the building. Okay, so to have something like this actually go all the way up to the top, okay, and ultimately get chopped off by the roof. Okay, actually, because really what I want to do is basically catch the roof plane as well as the second floor plane and carry them all down to the ground. So I should do the same thing about cleaning up what's happening over here in this wall. And ultimately, this thing is just going to get attached to the roof. So if I go back to the 3D, flip it around, and I can say attach that to the roof, you'll be in pretty good shape. In my structure only, I took out the walls, and I put the walls back in. Okay, there's that wall. If I want that to be a structural wall, I just need to turn on the structural capabilities, and then I can decide, does that need to be considered as a bearing wall or just a shear wall? Either one of those will work, depending on what load case you need. Okay, and that's enough to kind of do that. So what you're going to do is actually start putting in these lateral load resisting elements too, at least on all 4 sides, but we may need some more in the middle, and we'll kind of get to that. But we do that, and that's really how we start resisting the lateral loads. And as long as we have different resistance mechanisms in each of the different planes, we should be okay. But again, we'll analyze that and figure out where we got up. How much wall you need really depends on the qualities of the material you're using. Concrete reinforced, very, very strong. You probably don't need a huge amount of it. In a lot of light frame wood construction, what we end up doing is we actually use the plywood sheathing on the outside of the wood studs as our lateral resistance, and you have minimum lengths that are necessary, because plywood sheathing on the outside of the wall is good for like 240 pounds of lateral resistance per linear foot, something like that. Concrete reinforced much, much better. Steel, even better still, but there's some engineering behind it, and we'll go through and work through that. But what this will sort of lead us to is we're probably okay enough in our big building, in terms of, we'll have some here, we'll have them on the outside. Our building's not so big, but if you have a lot of lateral loads, because you have a very tall tower and you have to carry all the loads down from 50 floors, or you have a very, very big building, and the distance between the outside walls is too large so that you can't really count on the floor acting like a beam. It would deflect too much. You start adding these things called cores into a building, and that's where it gets really, really interesting. So if I needed to go ahead and add some structural support, and the outside walls weren't good enough, I needed to put some structural support in the middle of the building somewhere to kind of do that lateral resistance. You say, okay, I can do that. Let's go out, we'll grab a wall, We'll make it a concrete wall. We'll say let's make it structural in a second here. They have to place it first. Okay, I'm going to go through and put some sort of core in here. And I should actually make that go all the way up through the building. Typically these will go all the way from level 1 all the way up to the roof or something like that. Make that structural. Okay, and we have this ability now to put some walls in there. Now, the cool thing about these cores, or how they tend to work together in buildings, is if I need a wall that's going to run all the way from the base of the building all the way up to the roof of the building, okay, you think about the architectural features and what sort of things do that, there actually is a very logical place to put them. Things that tend to run all the way up to the building are elevators, which tend to have very straight walls. Stairways tend to have very straight walls going all the way up. You know, even mechanical shafts tend to have very straight walls going up. So what do we tend to do? If we're going to go ahead and have some sort of core to resist the shear, okay, we tend to use it also as the elevator and stairway and mechanical shaft too. Because it gives you this nice ability to go ahead and just have something and get a structural purpose as well as the kind of architectural and the mechanical purposes all at once. So think about in all your buildings, there probably is going to be a place where there's going to be a stairway running up, where relative to that, that's actually a fantastic opportunity for actually doing some of the lateral reinforcement too. It sort of all works together. So what we'll typically do is we'll go through and we have some sort of core like this, but then we'll add an element that we call a shaft to it. And what is a shaft? A shaft is really just a void. It's an opening. Put it in there. Make it go all the way up to level 3. Finish it. Okay. What the shaft actually does is it goes through and it cuts away floor and it cuts away roof. So let me see if I can do that. There's my walls over there. Hang on. Oh, I'm trying to come up with a way that you can actually see this. Let's go 3D. Let me turn on my little section box. That may make it easier to see. And I'll sort of scoot that over to where I think the shaft is more or less. There we go. So the shaft is actually now inside the core. Okay. Notice the shaft did a pretty good job. It cut away the floor for me just fine. It didn't cut away the structural framing. It doesn't do that. Shafts are good. They'll cut away floor. They'll cut away roof. They'll also go ahead and cut away ceiling. So if you have any of those elements, they'll cut them away. It's not so good on the structural framing, so what you have to do for the structural framing, though, is, in the same sense, come back over here, and I'll grab that structural framing system here. The cool thing is, since it's a system, I can edit it, and what I can do is actually just put a boundary on this thing. So I could go through and change its boundary to avoid the shaft. Do a little bit of trimming to make sure that looks good. Oops, that wasn't good looking. Finish that up. See what it does. Actually, those little tiny sort of K-joists on the side probably aren't going to be very happy. I'm just guessing because they're a little bit too small to actually generate. So I think that may give you some trouble. But let's see how this goes. It's still working. Okay, let's stop though and pause and sort of give you a chance to ask questions. So the whole idea of adding these like lateral either braces or adding some sort of walls, how's that sort of feeling? Because in your building, you'll need to have some lateral support too, and you can think about exterior walls, or if you have a stairway, and chances are you do, that's again a very good chance to go through and integrate it. Okay, looks like in this case my distances are so small, there's not enough room to go through and make the little cave joists. So in that case, what I probably have to do is, in the area around that shaft, I probably need to shift to a different sort of framing system. You know, in fact, even in here, you know, maybe since those are so short, what I have to do is just say it can't really be the K-joists instead. It has to be something simpler like the tube steel, or just something that doesn't have a repeated element to it. The K-joists are just problematic because in order to sort of generate the little spans and stuff like that, they're sort of a minimum length that they would have to be. Let me try that again. Edit the boundary. See if I can get it to regenerate it. Looks like it's sort of messing up on me. Okay. I'll leave that be for now. Okay. So we got these lateral load systems. We got the vertical load systems. You have a facade related to that. We are almost ready to do some analysis. We're not quite there, but we are almost ready. So let's kind of talk about that final step of how you actually do the analysis and you go with this. Because you've been working so fine just inside this system right now. You are ready for the final step. And that looks like this. So here's my little analytical model. Notice the walls are there. That wall's going over here. That wall's looking good over here. We're in pretty good shape. Okay. When it comes time to actually add loads to this, you can actually add loads in this model too. Okay, so let's talk about the loads that you need to sort of include. So there's different types of loads. There is the dead load of the building materials themselves. Okay. There are the live loads of us dancing around inside of here, you know, the furniture, the books, all these different things, they all get loaded in there. And there's all sorts of rules about the standard loads we use for different buildings. So, you know, we don't actually sort of do a very detailed calculation. We tend to use standards that say, like for most living spaces, most kind of common use spaces, the live load is 40 pounds per square foot. Okay, so for every square foot, we imagine 40 pounds here and 40 pounds there and 40 pounds there. And even though I weigh more than 40 pounds right now in this one spot, on average, that's probably going to work out okay because I only occupy so much space. So it tends to work out pretty well as a way to do it. For the live or the dead loads, based on the materials you're using, whether it's steel or wood, whether it's a concrete floor, stone on top or carpet, whatever it is, you know, we can go through and compute those. We can try and figure out per square foot what we think the dead load is, and just kind of add that all together. Live loads tend to be relatively higher for the living areas, less for the roof, interestingly, because your snow and your occasional rain, it actually isn't as heavy as we are in the scheme of things, so it's weird. You think the roof would actually have the worst load, but it doesn't. Unless you're in a really high snow area where it stacks up high, maybe you'd have it there. But you can start adding loads to this. Let me go through and flip it around. Actually, there's one loading condition you have to watch out for that I'm always stung by, because when I do residential construction, I'll often have balconies and sort of areas that are outside. It turns out they're considered much worse than your average living area. It's kind of weird. You think, well, how often are people out on the balcony? What's really going on there? But these tend to be designed almost for the worst case scenarios. And the problem with your balcony is it's that time when the parade's coming down the street. You have all your friends over who are at brunch at your house, and you're all hanging out there with your mimosas, kind of watching the parade go by, crowding up against each other to get the best view. At that one moment in time, you know, boom, then you get yourself in trouble. It's actually kind of interesting. If you start thinking about a lot of structural failures, it's often these times when it's parties, and it's times when people all get together. And it's, yeah, there really is a problem. It's sort of extreme use times, and you have to be able to kind of guard against that. Because a collapsing balcony is just never a good thing. Okay, but that's what often sort of happens. So let's talk about loads and how we'd add them in here. Loads, and we will go ahead and put some loads on your building and have you do a little bit of analysis to test these out. You can apply it in this way. What you got to do is go to the Analyze tab. Let's talk about creating some loads. And there's different types of analysis here. There's space reporting, there's systems reporting we'll talk about, there's energy analysis. We'll end up using a lot of these different things. Let's just start with loads first. Okay. There are individual loads that we can add, and there are also going to be load cases that combine them together. And let's just start with individual loads, and then we get to sort of the cases and how they get analyzed, ultimately, like in or how we combine them for the purpose of analysis. We can create point loads. We can create line loads. We can create area loads. Okay, so 3 different types, whether you sort of, and specific amount of loading on an individual point, a loading per lineal foot along the entire line, or a loading per square foot across an entire area. And within that, we have the notion of, do we want to go through and apply it ourselves manually, or do we want to host it? And hosting tends to be a pretty good thing. What that is that we're going to put the load on top of an element and let the element and its size figure out, how it's carried down onto the structure. So hosting tends to be a pretty good thing. But let us talk about how we can use this. Look at my little analytical model. He's looking pretty good there. Let me go to my structure only model. So I just need a surface to put this on. What I want to do is I actually want to go through and put some loads on the floor. So what I'm going to do is I'm going to visibility graphics, just turn off those walls, but I am actually going to turn on the floors because I want to see those for now. So I got my floor kind of hanging around in here. I'm not going to worry about that basement floor, the first floor, just yet, because we're going to figure out about that in terms of whether it's a slab or what's going to happen with the foundations of that in a little bit. But for the second floor area, let's start talking about it and what we want to do. We got a big floor area kind of all over, going to wrap around. We got a little bit of it. It's actually a balcony. It's going to happen out here. So let's talk about how we can go through and create these loads. And what you got to do is like this. You say load. You say that I want to make it a hosted. I'll make it an area load so that if I don't want to just make a load on a beam, I want to put it on an entire floor plane, I can make it an area load. And then we're going to put a basic loading to it. In the z direction, by default, this is considered to have -1 kips per square foot, so 1,000 pounds per square foot pointing down, which is a lot more than we need. That's what we're doing right now. If I want it to be 40 pounds a square foot, it'd be 0.04. Is that right? Yeah. I always have to think about that. Okay. And I can go through and say that's my load. Then what I'm going to do is come on over and find a surface that I want to apply it to and click on that surface. Yeah, it's not going to let me click there. Let me see what's going on in terms of if I have to make that structural. Structural. Let's try that again. Loads. Hosted area load. You going to take it now? Okay, beautiful. Now you'll notice I've applied this load. It kind of shows up with this little purple line all over the place, and it's kind of looking okay in terms of what's going on. Although it's not quite accurate yet because it's applying it to the entire floor area. It's also applying it to the balcony area, so that might be a little bit of a problem. We might want to separate those things. What can I do? I could go ahead and just go ahead and add another 20 pounds a square foot just in the balcony area, or I could go through and break it down into 2 separate floor planes, and maybe that's the way to do it. Let's think about that. If I zoom to fit. Oh, let's talk about this. I've done such a great job of creating a single floor plane there, but I'm at this funny point now where I actually wish it were 2 floor planes. I want to split it, right? You're doing a lot of construction. You start to figure out that it's really not one big slab. It's actually 3 or 4 slabs based on how you want to pour it. Let me show you a trick that is very useful in that case. I got my slab kind of hanging around out over here. Choose it. It's going to sound very weird. What I want to do is actually copy it and then actually paste it exactly back to the same place. It's going to sound really weird. Now why am I doing that? I actually have 2 right on top of each other, exactly the same location. But I'm going to change them now. And that's what I'm after. But it's really, sometimes rather than splitting and then having to recreate the other one, it's actually easier just to duplicate it and then adjust the boundaries of one and adjust the boundaries of the other so they kiss each other. Just right on that. Okay, so what I want to do is I'll grab one of the copies and say edit its boundary. And then for its boundary, what I can actually do is just trim, I'll trim this line to that line. Okay, and that's going to be, actually that's not it, is it? Hang on. What I should do is do it in the floor plan. Level 2 floor plan. Level 1 ceiling plan. Did I stop editing the boundary? I think I did. I did. That was not good. Come back out here. Okay. Edit the boundary. Go over to the level 2 floor plan. There we go. Level 1 ceiling plan. What I want to do is take this one and I'm going to back it off so it's just right to the surface of the wall over there. Say finish that up. Then, now that I've done that one, I can take this other one, edit its boundary, and basically cut it in the other direction. I'm going to cut it here to here, and I'll trim it so it's only this piece instead. Choose that. I'm just getting rid of excess now. So, sorry for the brief diversion. That's just all about trying to clean up two different things. Come on. Oh, it needs a span direction. Beautiful. Close it up. Okay, so now with that in place, we can go through, and I just have my 40 over there. Looks like it stuck to the one that was the balcony. I'll take that one and I'll make it minus 60. I'll take the other one and apply the load case out there and make that the 40. So we got two different loads. Then ultimately we're going to do the same thing to the roof. We'll go ahead and put some load on there of like 20 pounds a square foot or something like that. And that'll actually be enough to do the ceiling. So when we come on back, what we will do is we'll finish applying some loads. We are going to go ahead and put some footings and some boundary conditions down here at the bottom, because if we don't have boundary conditions, this thing's just going to move in space. We need something to sort of indicate where it's going to resist. Okay, so we'll put some little boundaries there, and then we'll actually be able to go through and analyze this thing. So actually not too awfully bad. So we'll leave that for next time. I'll just show you boundary blah blah blah. Oh, I'm not going to do it now. I'm going to get myself in trouble. So we will continue with that thread there. But in the meantime, so you will be ready, please do go ahead and on your structure, see if you can kind of at least get the framing for at least one of the floors pretty much worked out and how the columns there can support it, so that when we come on back on Tuesday, we can actually apply some loads to it, and you can actually see how to analyze it and see how the system will ultimately tell you what the sizes of all the framing members will be, and we'll start to understand whether your structures are stable or not. Okay? Okay, let us adjourn for tonight.